Hello guys, this is Sky Academy. Today we are going to look upon the concept of atomic number, mass number, and isotopic mass. Yes, we will continue to deal with the chemistry of senior 4, but we shall also look upon the other chemistries. But today, this is the topic of senior 4, secondary schools of Rwandan schools. Yes, so the concept of atomic number, mass number, and the isotopic mass. Yes, today when we look upon the atomic number, simply the atomic number denotes the number of protons in atoms nucleus. When you say atomic number, you say number of protons. So that is the atomic number. Then the mass number denotes the total number of protons and neutrons. The protons and neutrons are often called the nucleons. So mass number, it is the number of the protons and the neutrons in atoms nucleus. Then we needed to know how we shall write our mass number and the atomic number. Simply, it is written in this way. You have the elemental symbol. This is the elemental symbol represented by X. This X can be replaced by any element on the periodic table. For example, you can replace with the calcium. You can replace with the calcium, and then you put here the mass number, and then here we put the atomic number. When we say here A is the symbol for the mass number. It is the symbol for the mass number. Then it is written on the left superscript. Left superscript on the elemental symbol. And then this is Z represent the atomic number. It is written in a left subscript. Yes, that is those words what it calls. When you say by convention, the scientists sat together and then confirm that we shall write the element like this. That's why, for example, if you write calcium, we shall write like this, and then calcium it is 20, and then the atomic mass number is 40 and 20 here. So that is the elemental symbol, how it is written. For example, if it is hydrogen, write mass number 1 and then atomic number 1. The atomic number, you say it is equal to the number of protons, and then the mass number is equal to the protons plus neutrons. So some atoms of the same element have the same atomic number but different mass numbers. Such atoms are called isotopes. Some atoms have the same element, have the same atomic number but different mass numbers. Yes. You may ask yourself, normally atoms have the same atomic number but different mass number. But here we are saying the atoms of the same element. Atoms of the same element. For example, you can say oxygen. Oxygen has three atoms. Oxygen has 3 atoms of the same element. For example, oxygen itself has 3 isotopes. You say has 3 isotopes. They have the same atomic number but different mass number. So those atoms of oxygen said to be isotopes. Yes. Then isotopes, let's dive quickly to the meaning of isotopes. Simply, the isotope are atoms of the same element which have the same number of protons but have different masses. Isotopes are atoms of the same element which have the same number of protons but have different masses. Uh, Here, as I told you, for example, oxygen, you may have oxygen 16, oxygen 17, and oxygen 18. Oxygen 16 also have atomic number of 8. Oxygen 17 also have atomic number of 8, and the oxygen 18 have uh, atomic number of 8. Means that those three atoms have the same number of protons, or simply they have same atomic number, but they have different mass number. The first one has atomic number of 8 and the mass number of 16. The second one, the second oxygen, have atomic number of 8 and the mass number of 17. The third atom has atomic number of 8 and the mass number of 18. So those atoms are said to be isotopes. Isotopes. So to understand this, let's dive into the formulas. When you have mass number, it is equal to the proton number plus neutron number. Mass number is equal to protons plus neutrons. For isotopes, this proton number that do not change, but this neutron number changes. That's why if the neutron number changes, the mass number also keep changing. You understand this? Mass number is equal to proton number plus neutron number. In fact, we can say isotopes are atoms of the same element which have the same number of protons but different neutron number. Because we have seen that the neutron is the one which changes, but proton do not change. In fact, you can say that proton is the identity of an atom. When you say identity, is that thing that do not change? Yes. For people, you can change. You cannot. If you are Rwandan, you are Rwandan. If you change the country, you can move to another country, but you cannot change the country of birth. Means if you are born in Rwanda, that identity keeps moving with you. You cannot change. Yes. You can get another nationality, can live in another country, but the country you were born will remain the country. Also, the proton do not change. If you change the proton, means you change the atom. I think we are together. But the neutron number keeps changing for isotopes. For isotopes, we see that the neutron number changes and then the mass number also changes, but the atomic number remains the same. We can calculate the atomic number. Atomic number is equal to the neutron. It is equal to the number of protons. Atomic mass number is also equal to the atomic number plus neutron number, because the atomic number of seen is equal to the number of protons. So you can calculate the simple calculations related to these simple formulas. Yes. Here there is a simple question. Exercise 1. Use the list of the words given to fill in the blank space. Each word will be used once. We have atomic number, we have mass number, we have protons, electrons, isotopes, and neutron. So simply we are going to go together. The atomic number tells you how many. Yes, you have to fill one word here. in another word here. So atomic number tells you how many are in an atom. How many? How many? So there is something I want to tell you here. In an atom, we have seen the atomic structure in the earlier lessons. On the session is past before. We have seen that in an atom you have protons, neutrons, and electrons. And then in an atom also, protons and electrons have the same number in a neutral atom. I repeat once again. In a neutral atom, protons and electrons have the same number. And then neutrons, we have seen it keep changing. The neutrons can change, but protons and electrons have the same number in a neutral atom. When I say neutral atom, I said an atom which is not in a chemical reaction. An atom which is not in a chemical reaction. That is a neutral atom. But if an atom is in chemical reaction, means it has lost an electron or gained electron depending on its nature. If it is a metal, it loses an electron. If it is non-metal, it gains an electron, or there is a sharing, as you know, the chemical bonds. Simply, if an element lost or gain electron, means the electrons in fact have changes. But a neutral atom which is not in a chemical reaction has the same number of electrons as a proton. So the atomic number tells you how many protons and electrons are in an atom. Okay. Then here is the number written as subscript on the left of the atomic symbol. The number I have seen which is written as subscript is the atomic number. Atomic number is the number written as subscript on the left of the atomic symbol. Yes, as you have seen here, you have seen that the atomic number is the one which is written as a subscript on the left of the elemental symbol. So then another question is the total number of protons and neutrons in an atom is called the total number of proton and neutron is called the atomic mass or the mass number. Total number of protons and neutrons is called the mass number. Then the atoms with the same number of protons but different number of neutrons, yes, are called the isotopes. We have seen that isotopes are atoms which have the same number of protons but different number of neutrons or different mass. We have seen that they have different mass, and having different mass means that they have the different neutron number, because the protons do not change. Protons do not change, but the neutrons changes, and as the neutron changes, also changes the mass number. That's why here we are feeling isotope. Also, we need to add these S, atoms. Atoms. When we say isotopes are atoms, there are many. They are not one. If we say isotopes, the isotopes of an element means that you cannot say one atom. We say many atoms because they are many. They are more than one, which make up isotope of an element. So if you are writing, if you are writing the isotope, you need to add this plural form. Isotopes are atoms of an element, of the same element. Atoms, they need to be more than one. If you write isotope is atom, it means you have failed. So you have to write isotopes are atoms of the same element, then you continue with the writing. See? So, okay, we have another one. The subatomic particle that has no charge is called. This one also you need to know. You know the subatomic particles. Subatomic particle. The main ones are three. The main ones are three: protons, neutrons, and electrons. And the one which have no charge is neutron. So you fill here in a neutron. And then our exercise have finished. So we can continue with the session. Here we are going to calculate the relative atomic mass of element with the isotopes. So simply, if those elements have the atoms, main atoms, we need to calculate the relative atomic mass. Simply, relative atomic mass, I can say it is like an average. It is like an average of atomic masses of all the elements isotopes. As we have seen, if we say the isotopes are atoms, it means those atoms need to have an average mass. Because they have different masses, you need to make an average in order to have a common mass. That is relative atomic mass. So the relative atomic mass, so simply to calculate the relative atomic mass, you need to have this formula. You need to have this formula, relative atomic mass. The relative atomic mass, also you have to have what you call the abundance, abundance of an isotope, and then their atomic masses. To understand this, when you say abundance, I come to my example here. Oxygen contains three isotopes: oxygen 16, oxygen 17, and oxygen 18. This example simply shows that we have three isotopes of oxygen. The first one is 16, the second one is 17, the third one is 18. All those isotopes have the same number of protons or atomic number 88. We have said it earlier. So, to know the abundance, simply to understand what is abundance, those kind of oxygen are not in the same quantity in the atmosphere. For example, this oxygen 16 might be, or we are not suggesting that. Okay, we know by experimentally oxygen have shown that its abundance is 99.7%. In fact, this oxygen 16 is the one which is very more abundant in the atmosphere. This oxygen 16 is the one which is more abundant. It is 99.76%. This abundance, it says that which quantity of that isotope present in the atmosphere, if it is a gas. Which quantity? Simply we deal with the quantity. So this is 99.76, and then oxygen 17 is 0.04%, and then oxygen 18 is 0.2. The one which is the least abundant is this one, oxygen 17, which is 0.04, and then it is followed by this oxygen, which is 0.2, and then the more abundant is 99.76, oxygen 16. Okay, so I think you understand what is abundance. And then the atomic mass. When you say atomic mass, also we come back. This oxygen 16 has its own atomic mass, oxygen 17 has its own atomic mass, and oxygen 18 also has its atomic mass. But you are going to combine those atomic mass and the abundance together in order to obtain the relative atomic mass that oxygen, that all atoms of oxygen should do have in common. So the formula is this one: relative atomic mass is equal to abundance one for one isotope times the atomic mass one, and then plus abundance 2 times atomic mass 2 plus abundance 3 plus times atomic mass 3. You keep going like this until you reach to your final isotope. For example, if you have 7 isotopes, you can keep adding abundance 4 plus abundance 4m4, a5m5, a6m6, a7m7. But you say abundance n atomic mass n because we don't know how many isotopes each element have. But if any element you are given, also they have to give you the abundances and even the atomic masses. So we divide with the abundances. Abundance 1 plus abundance 2 plus abundance 3 plus abundance n. So this is our formula. Okay. So we have an example. In order to understand this clearly, you have an example. Yes, this example, oxygen contains 3 isotopes and then their respective relative abundance are this one is. Then calculate the relative atomic mass of oxygen. The question is to calculate the relative atomic mass of oxygen. So we have given all what we wanted to be given. Yes, we have given the atomic masses and even their respective abundances. So now we are going to calculate the relative atomic mass of oxygen. The relative atomic mass of oxygen here we have the relative atomic mass of oxygen 16, which is 16. Yes, this is relative isotopic mass. Relative isotopic mass, that is the mass of one isotope of oxygen, which is 16. So, and the relative abundance is 99.76. In fact, this oxygen 16. This is the relative isotopic mass, and then this is its abundance. The second one is 17, its abundance, and the third one is 18, its abundance. Then we are going to use our formula relative atomic mass. We say abundance 1 mass 1 plus abundance 2 mass 2 plus abundance 3 mass 3 over the total abundances. So we calculate, then we get this answer. This is the relative atomic mass of oxygen as we use today. Some people may ask themselves where that 16 came from. This is where it came from. It came from the average abundances the average relative atomic mass of oxygen's isotopes. So by applying the same formula, the relative abundance of isotopes may be calculated knowing the relative atomic mass of the element and the atomic mass of the respective isotopes. So here I can say that this example is a simple one, but you can also use another way to calculate either. You can calculate the abundances or atomic masses or relative atomic mass, depending on what you are given. So here we have another example, the example number 2. Chlorine contains two isotopes, 35 chlorine and 37 chlorine. Then what is the relative abundance of each isotope in a sample of chlorine if its relative atomic mass is 35.5? Okay, here we are given the relative isotopic mass of chlorine. We have 35 and 37. In fact, those are the isotopes of chlorine. Chlorine 17 and the chlorine 17 have 35 as the mass, and then 37 as its mass. Means that chlorine has two isotopes, and then also chlorine has relative atomic mass of 35.5. So what we are asked, it is to calculate the relative abundance. So here we need to figure out the way we are going to work this question. We know that the formula, the relative atomic mass is equal to M1 A1 times A2 M2 over A1 plus A2. That is the formula. Also, we have to know that when we add together the abundances, they have to give you 100. Yes, when you add together the abundances, you get 100. So here, because you don't know what clearly the abundance is, but we need to add some other figures. For example, you can say that if the abundance 1 is 8%, yes, then the abundance 2 will be 100 minus the abundance 1. You understand the formula? If the abundance 1 is 8%, means the abundance 2 will be 100 minus 8%. Because we said that the abundance should have to be 100. Have to be 100. So abundance 1, if it is 8%, then abundance 2 will be 100 minus 8%. And then we replace in the formula. The formula says that relative atomic mass you replace 35.5, which is equal to, then we take abundance 1. Then if the abundance 1 corresponded to this chlorine 35, then you multiply with 35 because this is its atomic mass, and then we divide 100 because abundance it is in percent. It is in percent. Then plus that abundance 2, which is replaced by 100 minus the abundance 1, as we said, over 100, then the times z, then the atomic mass of another isotope. And then after getting this equation, we are going to find the abundance 1. So you calculate this is the question of mathematics. Then you calculate you mix together in order to get this abundance. This is a simple calculation. Yes, the abundance 1 would be equal to 75. The abundance 1 would be equal to 75. And you said that abundance 2 is equal to 100 minus the abundance 1. 1. So we take 100, then you then 100, then you subtract with the abundance 1 in order to get 25%. So therefore, the abundance of the isotope of relative atomic mass of 35 chlorine is 75%, while that of the isotope 37 chlorine is 25%. So I think this is enough for the relative atomic mass. If you need any clarification, you may write in the comment. But this is a homework you can try. You can try yourselves. This is an exercise. You have 3 isotope of magnesium, and then there's abundances and there are masses. Atomic. This is your atomic mass unity. Then you can find the relative atomic mass. And also, you have another question here. You have atomic weight of gallium. The mass of naturally occurring isotopes are this one for 69 gallium, and then 70.9 for 71 gallium. Then you calculate the percentage abundance. So there's a question can help you to understand it clearly. So I think this is the end of our session. I thank you for a great attention. So, so I apologize for making voices which is not clearly. So thank you for your kind attention. Shall meet in the next session.